Hello, and today we're going through integration for the whole of A-level maths, so let's get started. So integration is the reverse of differentiation. And when you have dy over dx of a function dash of x, say it's ax times to the power of n, when you integrate it, you would go from dy dx to y, so you have y is equal to a divided by n plus 1, so you increase the power by 1, and you divide it by the new power, and this would be your final integration. But then you have to always add the plus c at the end, because when you go from this one into this one, so when you differentiate this, the c would get lost. So when you go backwards, you need to add that plus c. And the way you write it out, so you would just do integral of f dash x goes back to the original function f of x. So you write an integral like this with a squiggly line that goes down like this, and a dx after with your function here that you want to do the reverse of differentiation, so to integrate basically. And to find your c, if you have your values of x and y, you can substitute them into the equation to find your c. And if not, if you leave it as plus c, this is called a family of curves. So when they don't give you your x and y, you leave it as a family of curves, because different values of c will look like this. So if you have an equation with an unknown c, you can have an equation that represents this family of curves, because different values of c, for example here c1, c2 and c3, have different curves to them. So now let's move on to a question where they're asking dy over dx is equal to 6x squared plus 5x, and they're saying find the original function if minus 1, 1 is part of the curve. So first, we would write out the integral like this, as we said before in the formula. So we'll use this notation here. And to integrate this, we're going to, again, increase the power for each one and divide by the new power. So the 2 over here becomes a 3, and we divide by the 3, so we'll do 6 divided by 3. And then here is x to the 1, so this will become x to the 2, so x squared, so you do 5 divided by 2, which is the new power. And remember always to add your plus c at the end. And if you simplify this equation, you're going to get 2x cubed plus 2.5 x squared plus c. And now, because because we have this plus c here, and they tell us that the original function goes through minus 1 and 1, if we write out this equation, so y is equal to 2x cubed plus 2.5 x squared plus c, and substitute your y coordinate as 1, so over here, and your x coordinates as minus 1, you can get an equation where you have c, and you can solve for c pretty easily. So we would do 1 is equal to minus 2, so because the minus 1 cubed is just minus 1, so you do 2 times minus 1, which is minus 2, and 2.5 times minus 1 squared becomes 1, because you do minus 1 times minus 1, it will just be 1. And then you have 2.5, and when you collect these two like terms, you get 0.5. And when you take 0.5 on both sides, you'll get c is equal to 0.5. So now we know what c is, we can just plug it back into the equation. So we have the 2x cubed plus 2.5x squared plus c. You just plug it into the equation and you get 2x cubed plus 2.5x squared plus the 0.5 as you'll see over here. So now let's move on to finding the area under a curve. So this is very useful use of integration. So let's say you want to find an area between a and b of a curve that looks something like this. So you would use integration to find this area. And your notation will look something like this, where your area is equal to the integral of your function. So your function is this function in red, so this curve in red. And you integrate between your limits, so your upper limit would be b, and your lower limit would be a. So b and a. And this would be the notation. And what you do to this, so this is this notation just describes a type of definite integral. So this is a definite integral, and we'll explain why later. So no plus c is needed for this definite integration. So we won't add a plus c when we integrate this. And so how it works is that, say you integrate something like this and you get a plus c, then when you integrate with your limits, so with this function like here, you have your b and your a. What it actually does is when you get your, so when you integrate f of x, you'll get g of x plus c, for example. But if you apply your limit, what you do is you do your upper limit, substitute into your g of x plus c, and your lower limit, substitute into your g of x plus c, and take away those two together. So what ends up happening is that plus c over here and that plus c over here, they both cancel out. So you do c minus c, which is just equal to 0, as you can see. So the plus c is take plus c minus plus c is equal to 0. And you're just left with your whatever you integrated. So this function here before the plus c, when you substitute b in, take away g of, so the same function when you substitute a in. So this is how you do definite integration and how you find the area under a curve. So you integrate the function, ignore the plus c, substitute the upper limit and the lower limit into the integrated forms, and then take away both of them, and then you should find the area under the curve. So now let's move on to a question where they're asking find the area under y is equal to 2x minus 1 between x is equal to 2 and x is equal to 8. So first, what we will do is write our notation like this, where you do our 8 is our upper limit and our 2 is our lower limit. And we will need to integrate this function. So what we'll do is, remember, increase the power by 1. So we'll get this power is to the power of 1. So we'll do to the power of 2, so squared, and divided by 2, which is the new power. So we'll get 2 over 2 times x squared. And because we have minus 1, this would technically be x to the power of 0. So we increase the power, so we go to x. So we have minus x here. And because x to the power of 1, if we divide by the new power, it's just going to be x divided by 1, which is the same thing as x. And this notation as well, you can see I applied my limits 8 and 2 in just these square brackets here, just to keep it so just to know that we need to substitute into these later. So now I've simplified it, so the 2 over 2 gets is basically 1, so you get rid of that. And now I finally apply my limits. So here you have the 8 and the 2. So what you do is just substitute your 8 into this. So you'll do 8 squared minus 8, like over here. And then if you substitute the 2, you'll get 2 squared minus 2, because it's x squared minus x as the function. And you'll take both of them, so the higher limit, take away the lower limit. And you would get 45 squared units, which is the area under the graph. So this would be the answer to the question. So now let's move on to dealing with intersections when finding areas. So the previous example that we just did is when you have no intersections between the points. So say you have a graph that looks something like this, and it intersects between A and B, and you're trying to find the area in between. And you could have, so in this case, you have to make your limits the root of the function. So for example, remember the limits that we had before, your A and your B, you would have to find the intersection between the x-axis and substitute your limits into the integration as the intersection, just to find that. And then we would have another example where you have an intersection. This is very, very important to take note of, is say you have, you want to take your integration or find the area between A and B enclosed by the x-axis, for example. When you integrate, you're going to have to find the intersection in the middle, because when you integrate between these two parts and these two parts, one of the areas is going to be positive and one of them is going to be negative. So the problem is that when you add them, so if you integrate the whole thing from the start to the end, these two are going to take away rather than add up, so you can't really find the area enclosed by the graph. So what you do is find the area separately by doing from A to C and C to B, and then because you have your A1 and minus A2, for example, when you find the area enclosed, you're going to have to do the positive and add and basically modulus the negative areas and even the positive ones, because you're going to get a positive one in the end. That's to find your total area enclosed. So now let's move on to a question which we can do to get some practice. In this case, they're asking to find the area of y is equal to x squared plus 3x between x equals minus 1 and x equals 2. So our first thing would be to find if there are any intersections between these 2 points. So if we find the intersection between, remember, we need to, the graphs that we shown before, it was between the x-axis. So when you intersect with the x-axis, y is equal to 0. So we're going to make this whole function equal to 0 because y is equal to 0, which is equal to x squared plus 3x. And when we simplify this, we can factorize this to find the roots. We see that we can factorize this to get x out and the x plus 3 out, and this is also equal to 0. And once we take out the roots, so we'll find that x equals 0 is a root, and another root is x equals minus 3. And the x equals 0 is between minus 1 and 2, so that's where we're trying to find. So we know for sure that there's a root between the two. So we need to find the areas separately. So in this case, we would apply the modulus to both of the integrations. And as you can see, so this might be a handful to look at the start, but remember we're trying to find between minus 1 and 2. So we'll do our minus 1 to our 0, because we have to do from the initial point to the intersection or the root, and then we have to go from the root to the final point. And we're going to have to integrate each of these separately and add up the areas, the modulus of the areas, because one of them is going to be negative. And so in this case, so I did the integration over here because it's both the same integration, so we know what it is, and we know, so basically the x squared will increase the power to x cubed and divide by 3, or just multiply by 1 over 3, which is the same thing. And the x, we can increase the power to 2 and divide by 2, so you get 3 over 2. And then the plus c I put in red because we don't need it, but it's just a good habit to have for definite integration, which is when you don't have these limits here. And yeah, so the plus c is not needed. And so what I would do is just substitute the integrated forms of these, and remember, still apply my limits on each one. And what you would do from this point is basically, because we still have the modulus here, we would substitute our limits into each one of the functions. So the 0 into this one, and remember they're all the same equation, which is just the 1 over 3 x cubed plus 3 over 2 x squared, which is the integrated form of the previous function that we did. And 1 over 3, so we substitute the 0, the minus 1, the 2, and the 0. And because you do 0 to 2, so minus 1 to 0, so you do the higher limit, take away the lower limit, or whatever you get from the integration, and then modulus this. And then for the second part, you do the higher limit, take away the lower limit again, and you modulus this. And just to make it simpler, because you have 2 zeros here, we know that if we substitute in 0, our integration will be 0. If we substitute in minus 1, we'll get 7 over 6. And if we substitute 2, we'll get 26 over 3. So now we know the values of each of these. That's why I highlighted them in separate colors. So we know that this one's 0, this one's 0. The 7 over 6 will go into the purple one, and the 26 over 3 will go into the green one. And so now we can just write it very clearly, because we're summing up the area. So this is one area, this is another area, and we're applying the modulus. And as you can see, this one will end up being negative. So this one will be negative and this one will be positive, so it's very useful to use this modulus sign. So now we get both positive, and when you add them up together, you're going to get 59 over 6, which is the area enclosed by the graph and the curve that we were looking at before, because there was an intersection between the curve and the x-axis. So now let's move on to year 2 integration. So we've done all of year 1 so far. Reverse chain rule. So reverse chain rule is a bit technical, but the basic idea is if you have something that looks something like this, if you have a function that looks something like this, you can really apply chain rule in reverse. So you would imagine this is your u, so your u in chain rule, and you would increase your power by 1 and divide by whatever, because when you multiply by, when you do chain rule, you multiply by the a, because when you differentiate this, you're going to be left with a. So because this integration, you'll do the opposite, so you divide by a and divide by the new power as well. So that's why you have this. This is a bit technical. There's another way of doing it, which is a lot better, but it's good to know this if you're in a rush and might need it. And we can explain more with practice. And this process of doing the chain rule in reverse is called the consider then scale process. And again, as I said before, this is explained way better in an example. So let's go on to the example. So say we have a integral, they're trying to find the integral of 4 times root of 7x minus 3. And say we have, so the function that we have inside is 4 times root 7x minus 3, which we can write as 4 times the 7x minus 3 to the power of a half, because the square root is the same as to the power of a half. And because in integration we normally add the power, so we can just consider, so this is our considering part, remember, from considering and then scaling. Because this part we're considering, because integration, we're going to have to, we'll just like add the power by 1 and see what happens. And when we add the power by 1, we'll get 3 over 2, and then 7 times 7x minus 3, and then all to the power 3 over 2. And this is like our trial, so we'll basically trial this function as our integration. So we're assuming that this integrates into something like this, very similar, because in integration we normally do add the power by 1. And so now, just to test that it's the same, that it's actually the integration, we can go backwards and differentiate this function and see what we get. And if we do get this, that means that we've guessed it very nicely, that this function here is actually the integration of this function. So to integrate that, so to differentiate this, we'll have to do chain rule. So we have to do du over dx times dy over du. And before looking at integration, I would really recommend looking into differentiation, so you have a strong grips before you get into it. But we'll do chain rule, so our u would be 7x minus 3, and if we do du over dx, we're going to find that it's 7, because if you differentiate this, you're going to get 7, because this goes away and this power decreases, so you're left with a constant 7. And your dy over du, which would be, say, because you made your u this part over here, so your function would be 4 times u, which is this, to the power of 3 over 2. So when you differentiate this, you would decrease the power, so you get a half, and then multiply by the old power, so 3 over 2. So you do 4 times 3 over 2 times u to the power of a half. And if we multiply this out and substitute our value for u, so we'll get 4 times 3 over 2, we'll get 6. And if we substitute our old u, which we said was 7x minus 3, substitute in the equation, we'll get our dy over du. So now we have du over dx and dy over du. We can find dy over dx. And we know that if we multiply these together, we'll do the 7 times 6 times 7x minus 3 to the power of a half, which is square root basically. We will get 7 times, so basically this function here, 7 times 6 to the power of, times 7x minus 3 to the power of a half. And once we know this, this isn't the same as what we suspected the integration was, because remember we assumed that this would be the integration, but when we differentiate this, we're getting this, which is not really the same as 4 square root 7x minus 3, but it's very similar. So as you can see, if we simplify this even further, we're going to get 42 times 7x minus 3 to the power of a half, which and our goal was to get 4 root 7x minus 3. So this is what we're trying to end up with. So from a function here, which we guessed was this one, we're trying to get a differentiation that leads up to this, so we can find the integration of this as our original function. So we put them back together and we see that 4 times 7x minus 3 to the power 3 over 2. So if we differentiate that, we're going to get the 42 root 7x minus 3, which is very close to our goal, but it's not the same. So what we can do to both sides, because remember that when you multiply by a constant, you can really take out of the differentiation and you can also do this for the integration. So if we multiply both sides by 4 over 42, you can divide this 42 and multiply it by 4, and then do that to this side as well. And now you have 4 over 42 times your differentiation of your guessed function, just by what we did was increase the power. And now this whole thing differentiates into our original, what we're trying to find, the integration. So that therefore this must be the true value of this when you integrate this. So because of differentiation, you can take out the coefficients and put them inside. We do this, and when we multiply by 4, we're going to get 8 over 21. On the inside, when we multiply 4 over 42 times 4, 8 over 21 on the inside, times the same 7x minus 3 to the power 3 over 2. And when you differentiate this, you're going to get what we expected to get, which was 4 root 7x minus 3. And remember, because integration is the opposite of reverse of differentiation, we know that if you integrate this function, you're going to get this. So now we know that if you integrate this part here, so we get rid of the differentiation and move it to this side, we'll integrate this side. So when you integrate this side, you're going to get this function, and just remember to add the plus c. So this is how we found the integration of this function here, just by increasing the power by 1 and then multiplying each side so that it fits correctly. And we know that this will differentiate into this, and this will integrate into this. And this is the final answer. So now, if we do a recap of reverse chain rule and how it works, you can look back onto the video and see how I did each step, but I'm going to go through each step what I did right now. So remember, in reverse chain rule, we're trying to find the integration of a function, say f of x, and we're integrating it in terms of dx. So what we do first is assume another function that is very similar by, say, increasing the power d over dx. When we d over dx, we'll get something very similar to f of x. So we assume a function. And so this is our consider step. And once we do that, we have to change both sides, so we get another function that actually, when you differentiate it, you get your original f of x that you're trying to integrate. And once you find this function, your h of x, which I just called here, you can do h of x plus c, just add the plus c at the end, and this would be your integration of the function that you're trying to find. And this is reverse chain rule. And however, but you have another way of doing questions like these, and it's called integration by substitution. And this is my preferred method because it's less about considering certain things, but more about substituting other variables to find out what the function, or so the integration of a function actually is. So now let's move on to finding the area between two curves. So we're done finding the area between or under a curve, and also when there's intersections as well. So now we are going to find the area between two curves. So something like this. Say you have a curve that looks something like this, and another one like this. And say you want to find the area between these two curves. So how would you do this? So first of all, very important, the two curves don't overlap. They wouldn't ask you if they do overlap for A-level maths. So it's very important to know that they don't overlap. You can use this formula if they do not overlap. You'll do the integration between b, so your upper limit, and a, your lower limit. And what you would do is do your upper function, which is f of x, and say your lower function g of x. You do f of x, take away your g of x. And then when you integrate this whole function together, you'll get the area between the two graphs. So now let's move on to a question. where we can apply this. And the question is asking, find the area between y is equal to x over 3 plus 2 and x squared, so also y is equal to x cubed plus 2x squared plus 3. And we're trying to find the area between the two curves between x is equal to minus 2 and x is equal to 1. So first, let's draw this out. So you can use your graphical calculator if you have one. And if not, you can assume how you understand the curve because of your function. This is a cubic and the other one's a straight line. But if you have a graphical calculator, make sure to use it because it's very useful. And now from this, you can actually see that your function that's on top is actually your cubic, and your function underneath is your linear function, so your straight line. And this is how to make your f of x and your g of x from the formula that we said before. So here I write the formula down. So your f of x would be the cubic and your g of x would be your straight line. And once you plug in your functions into the formula and your limits, remember, so because we're trying to find between your upper limit as 1 and your lower limit as minus 2, your b would be 1 and your lower limit a would be minus 2. So you substitute that all into the equation, and we can collect like terms, and you'll get x cubed plus 2x squared minus x over 3 plus 1. And this is the when you take like terms of taking away both of the formulas. And now all that's left is to integrate this function. And remember, when you integrate, you increase the powers by 1. So here you have x cubed becomes x to the power 4, x squared becomes x cubed, and x becomes x squared because this is x to the power 1, and the 1 becomes x because this is x to the power 0, x to the power 1. And remember to divide by the new power. So I've done it in red to try to keep it as clear as possible. So the new power is 4, so you divide it by 4 for the x cubed when you integrate it. And the new power is 3 for the x squared, so you divide by 3. And the new power is x squared, so you divide by 2. And then because when you have a constant, you would go to x. And because the power is 1 here, you divide by 1, which is the same thing. And remember to always apply your limits, your 1 and your minus 2 in this format here. It's just nice and easy to see. And all that's left now is just to substitute our limits and take away each of them. Because remember, when we have definite integration, we do 1 minus, so do the upper limit, take away the lower limit, and the integration of each, and take away each one. So we basically substitute that into the formulas here and taking them both away. And don't confuse this between taking away f of x and g of x from the areas on the graph. This is just for the definite integration. And once we do that, we apply the powers, we get this function here. You can see, you can check this, pause the video and check this, but I'm going to skip through. And yeah, this is each of the steps that we've done. So apply the minus to each of the ones in front. If you want to do this as practice, so use this if you need help. And we get a final answer of 23 over 4 as our area between the two curves. And you can write units squared for the units. So now let's move on to trapezium rule. And trapezium rule is used to approximate the area under a graph. And say you have a graph something like this. Instead of finding the area using integration, they might ask you to approximate the area using this trapezium rule that we talked about. And what it is basically splitting up the graph into these trapeziums. We'll talk about this after. But splitting up the area under the graph into trapeziums of equal height, and finding the area of each one and then adding them up all together. And there's a generalized formula, which is this one. You can look at it, you can pause the video and look at it, but I also prefer another way, which is using a table. So I'll explain this using a question, and we'll do this question where we are told to approximate the area under the graph of y is equal to x over 1 minus x squared, the square root of 1 minus x, and between x equals 1 and x equals 1.5 using 5 strips. So they're asking basically to use five strips of these trapeziums that we said over here. And so what we'd do first? So first we would see what is the height of each strip, and that's important to find the area of a trapezium because we need to know the height. And to find the height of each strip, we'll just do the difference between 1 and 1.5, which is 0.5. And because we have 5 strips, we're going to divide this by 5 to find the height of each strip. So we do 0.5 over 5 divided by 5 is equal to 0.1. And we can write a table. So this is what I talked about, the table that I really like. If we do a table, we can write out all our x values from 1 all the way up to 0.5. And we can see that there is a gap between each one of 0.1, and here we can get 5 strips from 1 to 0.1, so 1 to 1.1, 1.1 to 1.2, 1.2 to 1.3, 1.3 to 1.4, and 1.4 to 1.5, and here we should have 1, 2, 3, 4, 5 strips of trapeziums. So our next step is to find the height of each trapezium, or like the different widths of the trapezium. So we said the height was 0.1, so we need to find the widths of each trapezium. So you have the width at the bottom and the width at the top. So it's very useful to know the y values at each point. And I've done this using just the formula from before, and substituting your x value into it and finding out what you get. Some of them were very long, so I just kind of rounded them to have them together. And yeah, remember your height is 0.1. So when looking at the formula of a trapezium, we have so this is our trapezium, remember. So we have the height, which goes this way, and we would have our first y value, which is one of the widths, and then the second y value, which is another width. So to use trapezium rule, we'll use all our y values, so this one and this one, so from this row here, and we'll plug them into the equation to find the area of each trapezium. So because we know the y value of one side and the y value of the other side, for example, for this trapezium here, we can know, and we know the height is 0.1. So for this trapezium that goes from the 0.1 to the 1.1, we can just plug in the y values, so the root 2 over 2 and the 0.759 into this equation, and the 0.1 as the height. We can find the area of this trapezium, and then we can apply this to this one, this one, this one, and this one, so we get all the 5 strips at the end. So once we do that, all we do, so we have to add them up together. So I've done that. So I've substituted all the y values and the heights into the formula of a trapezium, the area of a trapezium. And when we add them up, we will get a nice approximation for the area under the graph. So when we add them up, we're going to get something like 0.4156. You can also try this question and just pause the video and look at the working out. And in the end, I approximated, so I rounded my value, because it was very long, to 0.416, and this is an approximation for the area. It's not the actual area. To find the actual area, we would have to integrate it, and you can actually check on your calculator. If you know how to integrate on your calculator, you can or integrate this function, you can check your integrated function compared to your approximation and see if it's close and if it's larger or smaller. So now we've done trapezium rule. Let's move on to integration by substitution. So integration by substitution is remember when I said about the reverse chain rule that I didn't really like it and I preferred a different method called integration by substitution. And this is the method, and this is a really lovely method. I love this method so much. So it's when you have a complicated expression in terms of x, you make it into an easy expression in terms of another variable, say u. And I want to explain this with examples, and we'll do the same at the end, and then just look at each step and make it clear at the end. But let me explain it with an example. So first, let's try this example, where you're trying to find the integration of this kind of very complicated function, where you have x times the square root of 2x plus 1 dx. So instead of trying to integrate this as most difficultly as we could try to, we can just make it a lot easier by just saying that a new variable u is equal to 2x plus 1. So this whole thing, we can just substitute it with a u, which just makes it so much easier. And now, what we will need to do is find our du over dx. And if we just differentiate this u function, we will get that. And we'll get that the du over dx is equal to 2, because when you differentiate this function here, you're going to be left with 2. So you know that du over dx is equal to 2. But now, I'm sure you don't know how to do this in differentiation, but you can actually do this. So you can rearrange this as if it was a fraction and move it, so multiply by dx on both sides, and you'll be left with du on one side times 2 dx, and then rearrange it again, so you move the dx on its own, and you have du over 2 is equal to dx. And you see this dx that we had in integration, in our notation for integration for this whole time. This is what we're going to have to substitute, so we differentiate in terms of u instead of differentiating in terms of x. So we have a much easier function to integrate. And also, because we have this x, it's also worth rearranging this equation and making x the subject. So if we need to, which in some cases we don't need to, but we'll get to that, you can just substitute this straight into here and it'll make it much easier. So you get rid of all x's, and because x is a variable and you don't want it there, so we'll just substitute this into the x just to get rid of all the x's, and we leave it in terms of u. So how does this look like? So this is the function that we're trying to integrate, and if we substitute our x as what we said was x in terms of u, and the 2x plus 1, we can just substitute it straight as a u, and the dx, remember, we said because of this crazy fraction of du over dx, we rearranged we can say that dx is du over 2, so we substitute that in as well. And now we have an integration. This integration, it might look difficult, but it's very easy. And you can integrate this in terms of u very, very easily. And so I rearranged it just to make it look a bit better. So the 2's, I collected them together. So I have u minus 1 over 4, so 2 times 2 basically, times the root u. And we're integrating in terms of u, so the du at the end. And because when you do this, the square root is basically to the power of a half, so we change that, and now is where it starts to look really easy to integrate. So now if you multiply each of the sides, so because you multiply this times this, you would multiply the u to the half times the u and the minus 1. When you apply this, so you open up this bracket basically, you would get u 3 over 2 minus u 1 over 2 all over 4. And this is very easy to integrate because you have two separate values or two separate terms here, which are very easy to integrate. And what you have to do is, so what you can do integration is take out the coefficient. So we have this 1 over 4. We can just take it out very nice and easily. And you're just left with u to the power 3 over 2 minus u to the half. Integrate in terms of u. And once you integrate this, remember to add your plus c, and you increase both powers by 1, so you get 3 over 2 becomes 5 over 2, and a half becomes 3 over 2. And then divided by the new power, so 5 over 2, you get 2 over 5 times 2 over 5, and the 3 over 2, you multiply that term by 2 over 3. And remember to have the 1 over 4 on the outside because we haven't changed that. And remember to add your plus c. And if we multiply both terms by the 4, so open up the brackets basically, we get 1 over 10 times u to the power 5 over 2 minus 1 over 6 u to the power 3 over 2 plus c. Very nice and expanded out. But now, because they asked us to differentiate in terms of x, or like integrate it in terms of x and leave it in terms of x, we'll substitute back what our u value was from before. So we'll substitute our u as 2x plus 1. So this was our integration in terms of u. Let's just substitute our x value back. And this will be our final integration for the question that we had before, which is and this is exactly how they would expect you to do these kind of integration by substitution questions, which is very straightforward, as you can see, compared to the reverse chain rule, which might have confused a lot of people. But they might ask different ways of doing this integration in the exam, so it's good to know both actually. But this one is clearly very superior. I just want to go through another question where we have definite integration now. So in this question, they're asking to find the integral between 2 and 0 of this function here, which is x squared multiplied by the square root of x cubed plus 5, and we integrate in terms of x. So how would we start this out? First, we would make our u, because we're using integration by substitution. Our u is equal to whatever's inconvenient in our case, which would be the x cubed plus 5. So the inconvenient is this part here. And then after, we would have to make our find what du dx is. So u is equal to x cubed plus 5. So du of dx, when we differentiate this, we're going to get 3x squared. And if we rearrange the equation, we're going to get du is equal to, so rearrange this fraction or differentiated fraction so that we get du as the subject is equal to 3x squared plus dx, but we want dx as the subject, so we rearrange again, so divide by 3x squared, and we're going to get our dx as du over 3x squared, so we can substitute the dx into the integration here. And then what we do next is to find, because in integration by substitution for indefinite integrals, we would have to change our limits because these limits are in terms of x. So what we do is find what our u is in terms of these limits. So u is equal to x cubed plus 5, and because we're looking between x equals 0 and x equals 2, we would have to substitute our x into this function here. So we're going to substitute 2 inside and 0 inside, and we're going to get two different values for our upper and lower. So we know our lower is 0, so when we substitute in, we're going to get our lower for u as 5, and if our upper is 2, we're going to substitute into the value of this equation for u, and we find that our upper value for u is 13. So we can substitute into these as well. And if you get any function, so say you substitute a larger value for x for the upper bound, and you get a smaller value for u than the lower bound, always keep the upper bound the same and the lower bound the same. So for example, if you have a function where you put in 2 and you get out minus 3, and if you put in 0 here and you get 5, for example, because minus 3 is less than 5, you would think to put the 5 as your upper bound and minus 3 as your lower bound, but actually keep it the same because the 2 is larger and the 0 is smaller. So keep your upper bound the same and your lower bound the same to the same corresponding value, basically. So once we've found this, now what we do is just substitute everything back into the equation. So in this case, so we substitute our limits, so the 13 and the 5, which correspond to the 2 and the 0 for the x values, and these are in terms of u, so very good. And now because the inconvenient function, we substitute in u instead, so we have the square root of u. And then because our dx we said was du over 3x squared, we write it in here. And remember, we still have this x squared inconvenient, and we also have this x squared inconvenient, which looks really easy to simplify out. So in this case, the x squareds actually cancel out, unlike the previous case where we had to substitute a different value for, so rearrange u to find x the subject and substitute the equation of u as x. In this case, the x squareds cancel out, so it leaves it nice and simply in terms of u, the whole integration. And once we have, so this integration is the square root of u over 3. We just need to integrate this, and the square root, remember, is the same as a half, so we increase the power, to the power of a half, and we increase the power to get 3 over 2, and then divide by the new power, which is the same as multiplying by 2 over 3, which is the opposite of 3 over 2, or like the flipped version of it. And we still apply our limits like this in this format here. So this is our integrated form in terms of u, and because now we have it in u and we know the limits in u, if you multiply this out, so 2 over 3 times 1 over 3, or the divided by 3, you get 2 over 9. And if you substitute in your limits, you're going to get the definite integration. So you have this, or you substitute your limits and take away each one, and your final answer would be 7.93, and it will carry on, so I just rounded to 7.93. And as you can see, we don't go back to x in this case. Before we did, because we know limits in terms of u, we can just substitute them straight in to find a final value. So that's the answer to this question over here. So now let's move on to integration by substitution recap. So we've done, remember when I said we're going to explain this by using examples, so and now we're just going to recap of all the steps of how to do integration by substitution. And I really recommend understanding how I went through the examples to understand this part here. So the first step would be to find what u is. So you remember, you make your inconvenient function where you have a complex function in terms of x, say under a square root or under a power of a really weird power. You would substitute that as u to make an easier integration. So you'll find your u first and write in terms of x, and then find your du over dx, and then make dx the subject because you're trying to substitute it back into the integration. And once you do that, if you have a definite integral, you want to find your limits in terms of u instead of x, because your limits would be in terms of x in the question, so you want to turn them in terms of u. This is only for definite integration. For indefinite integration, you don't need this. And the fourth step would be to substitute your du, and if you have definite integration, your new limits, that's why I put in green, and put this all into the integral and eliminate any x that is left by either making x in terms of u and substituting that into any x that's left over, or it should cancel out if you have a fraction, like say the du divided by x squared or x cubed or something like that, and it will cancel out, and yeah, get rid of any x left, which should be straightforward. And the next step would be to integrate in terms of u, which this is the reason why we've done all of these steps anyway. It's just so we have a nice and easy integration in terms of u. So this should be just simple integration. If you know your integration well, this should be very straightforward. And then the next step would be to substitute u in terms of x and add the plus c, and this is only for indefinite integrals where you don't have your limits. And so you can find your final value by just substituting your whatever you said your u was in terms of x, substitute that back in, and then so you have your final expression in terms of x, and also you have your plus c at the end. And for definite integration, you would need to substitute your limits in terms of u, so your u limits into the integrated form of in terms of u to solve the definite integral. And these are all the steps for integration by substitution. So now let's move on to integration of standard functions. So it's good to know the integration of, like, for example, if you know how to integrate x squared, x cubed algebraic functions, that's pretty easy. So there's other functions that you might need to know how to integrate. For example, if you have, so this is the simple algebraic function, and if you have something else like e of x, when you integrate that, it literally just stays the same. So it's just e of x. And if you remember from differentiation, if you differentiate e of x, you'll also get e of x. So it's the same as going backwards, but always remember to add your plus c. We've done this with the simple algebraic functions where you increase the power and divide by the new power, and then always add your plus c. And when you have 1 over x, for example, you would integrate it actually. So this would be the same as x to the minus 1. But if you, because we're increasing the power, when you increase the power, you get x to the 0. But actually, when you integrate it, you'll get ln x. And this is a modulus sign for everything inside the ln function, because when you ln a negative number, that's not possible. And remember to add your plus c. So it's really useful to know, especially this one's really useful, and this one's also very useful. So when you have trigonometric functions, you have sine differentiates into cos, and cos, when you integrate it, you'll turn it into sine, and also add your plus c, because you might have any constants when you differentiate it left over. And these are for if you have done second year trigonometry, sec squared x dx. When you integrate this, you get tan x plus c, and a lot of these will be in your formula sheet. And then when you integrate sec x times tan x, you get sec x plus c. These are also pretty useful, and they will ask a lot of questions in the exam. And then cosec squared x, when you integrate this, you would get minus cot x plus c. And for this, you will need to know second year in trigonometry. And lastly, cosec x times cot x is when you integrate this, you'll get minus cosec x plus c. And yeah, as I said, this will be in your formula sheet, but check with your exam board because different exam boards have different formula sheets. So now let's move on to a common pattern in the reverse chain rule, which is super useful. I cannot stress this enough, and this will come up a lot in your exam. So this is the basic formula. It's very straightforward. If you have a function at the bottom, so say you have a fraction where you have a function at the bottom and the function at the top is an differentiated form, of the function at the bottom, you can integrate this whole thing very easily into a form where you have ln and then the modulus of the bottom function here, and then you always add your plus c. And as I said, this is very useful. I cannot stress this enough. And remember we said before that when you integrate 1 over x dx, you'll get an ln form. This is just a more general version of it because you have a function at the bottom instead of the 1 over x by itself. So now let's move on to a question to see how we can apply this. So in this case, we have the x squared at the top, which looks like a very similar, so it looks similar to the differentiation of this, but it's not the same. So what would be our first step? So our first step, we try to integrate this, but it looks kind of complicated. We'll use the formula from before. But if we can just multiply the whole function by 3 over 3, so 3 over 3, so times by 3 and divided by 3, which is the same as multiplying by 1, it's the same thing. We have this 3 at the top, so 3x squared, and then we can leave this 1 over 3 outside of the function. And now this part here, as you can see, it looks like the differentiation. So this looks like the differentiation of this, because if you differentiate this, you'll get this. So differentiate x cubed plus 2, you'll get 3x squared. So be aware of that. But we have this left over here. And remember, yeah, so as I said, so the differentiation is 3x squared and the function is x cubed plus 2. And because of integration, you can take out the coefficient really easily. And now you're left with just this to integrate, which is very, very easy to integrate because of the function or the equation that we looked at before, where we have the ln form at the end. And literally all we have to do is just integrate this part and multiply by whatever we had left over. And remember, you do the ln of the modulus of the bottom function, which is x cubed plus 2, modulus closed. And then remember to always add your plus c. And that's it. And look how easy we managed to integrate this function. So now let's move on to trigonometric identities to integrate, using trigonometric identities to integrate. So this is very useful. So if you have a complicated function in terms of trig, you can simplify it by using trig identities, which is covered in year 2 trigonometry. This is one where you have the sine squared plus cos squared of a value or a value a. It will always equal to 1 as long as this is a and this is a. And then you have the double angle formula, which is also very useful for integration, where you have sine 2a is equal to 2 sine a cos a. And this, if you've looked at year 2 in the trigonometry, you can derive this easily from the compound angle formula, which is given in your exam. And then also you have the cos 2a is equal to cos squared a minus sine squared a, which you can also derive from the compound angle formula. But if not, you can really memorize these two formulas pretty easily. And then you have the tan version of it, which is a bit more harder to memorize, but you can still memorize it. And you can also use the compound angle formula to find this equation for double angle formula. And yeah, it's good to look at year 1 and 2 trigonometry for these kind of things, because you have more trigonometric identities, which will be very useful for integration for the steps that we're going to do now. So we're going to do a question now. So for example, for this, yeah, I would recommend looking at year 1 and year 2 integration, but let's try this question. So it's asking us to find, so this is a definite integration where we have the upper limit as pi over 3 and the lower limit as pi over 6, and we are trying to find the integration of sine squared of 3x and then in terms of dx. And So our first step would be to find any trigonometric identities which have the x squared, because when you have a squared of a trig identity, this is a nightmare to integrate. So first comes to thought is the cos 2a in terms of cos squared and sine squared, and here we have a sine squared, so it must be helpful to rearrange to leave it in terms of cos 2a, for example. And then there's another equation where we can simplify this equation. So there's other forms of this equation, because using this trig identity here with the cos squared plus sine squared is equal to 1. If you rearrange this, you can leave the sine squared with the 1 on one side and the cos squared as the subject. And now, because you have this cos squared as the subject, you can substitute this whole function where the cos squared is in here. And this joins it into one big function where you make cos 2a the subject. And this is a lot easier to integrate, as you'll see later. So, and we're just trying to leave it in terms of sine squared, so we can substitute a different function into the sine squared 3x that we have here. And collecting like terms, we've got cos 2a, is equal to 1 minus 2 sine squared a. And here we have the sine squared a, which we can make the subject in terms of 1 minus cos 2a over 2. Really easy, we can just plug this in and make our a 3x. So remember, we have, this is the question, and if we substitute it in, in terms of the sine squared a, if we make our a the 3x, so we can substitute our function that we found here and make our a 3x, and then put it back into the formula here instead of the sine squared 3x, because say your a is 3x, this would be the same. It'd just be the same identity written as a different cos form, or as a different trigonometric form. And now this is a lot easier to integrate. So this, first of all, we can just separate out the two terms where we have the half divided by 2 of the 1 and the cos, and then we have half minus a half cos 6x. So this is a lot easier to integrate, as we can see it. And now it's just basic integration by substitution. This would be perfect practice, where you make your u 6x, because it's kind of inconvenient there. And if you make your du over dx, if you differentiate this, you'll get 6. And rearrange it so you get dx the subject, so you'll get du over 6 is equal to dx, so you can substitute it in there. And then again, your limits, you would have to change them to be in terms of u. So your upper limit would be 6x, which would be 6 times your upper limit, which is pi over 3, and 6 times your lower limit would be 6 times pi over 6, and your upper limit would be 2 pi, and your lower limit would be pi. And now all we have to do is just substitute everything back in terms of u. So our limits in terms of u now, and our new function in basically the same in terms of u. So with the 6x just becomes a u here. And we divide the du, so dx is equal to du over 6. So we write the du over 6 here. And now, because we have the halves and the sixes, we can or 1 over 6 basically, or divided by 6, we can just take that out. So divided by 6 is the same as 1 over 6, and then times a half, which both of the terms have. And because the fact that integration, you can take out any coefficients, and then we're left with a really easy function to integrate. So all we have to do is just, so a sixth times a half is just 1 over 12, and that's the outside, and the inside stays the same, which is just the limits 2 pi and pi, and integrating minus 1 minus cos u du. And yeah, keep the 1 over 12 on the outside, because we haven't done anything to it, but we integrate the inside. So increase the powers by 1 for this one. So 1 is basically u to the power of 0, so this becomes u to the power of 1 divided by the new power, which is 1. So it's the same thing, so divided by 1 is the same as itself. And then when you integrate minus cos, you get minus sine, because when you differentiate sine, you get cos, and because of the minus, it doesn't change. You don't really, it's like the coefficient on the outside is the same as multiplying by minus 1. So sine differentiates into cos, so minus cos differentiates into minus sine. And what we do next is substitute our limits into the equation. So we have the 12 on the outside, because we haven't changed that yet. And we substitute the 2 pi into the equation as u. And so we'll get 2 pi minus sine 2 pi, all in one brackets. And then we take away what we get when we substitute in the lower limit. So pi minus sine pi. and these are the integrated forms when you substitute the limits in terms of u. And here we're going to solve for the sines. So sine 2 pi is equal to 0, and sine pi is also equal to 0. So in the end, we're going to get a 12th on the outside, and then 2 pi minus 0 and pi minus 0, which is just the same as a 12th times 2 pi minus pi, which is the same as a 12th times pi. So the answer is pi over 12 for this type of integration. So another form of doing integration, if you have a complicated function, is to use partial fractions. So when you have partial fractions is when you have a difficult fraction in terms of x to differentiate. You want to integrate, you would leave it into an easier, more fractions, which are easier forms to integrate by using these two rules. So you would first do your partial fractions and then use this rule, remember, where you've got the differentiation of a function on the top and the function itself at the bottom, and you can easily integrate it in terms of in an ln form. And then this also other function where you have 1 over a x to the power of something. It's just basically as writing it as x to the minus 2, and then you would increase the power, so minus 2 increase the power to minus 1 and multiply by the new power, or divide by the new power, so divide by minus 1, which is the same as multiplying by minus 1. And remember to add your plus t's at the end. And these two rules are very useful for partial fractions. And if you don't know partial fractions, which we're going to use to integrate in this case, it's very helpful for you to go over year 2 algebra first, because this is where you learn partial fractions. And once you get to know them, this should be very straightforward, because it's just partial fractions and then applying it to integration. So now let's try a question. So this is the question, and it's asking to find the integral of this crazy fraction, which looks extremely hard to integrate if we didn't know how to use partial fractions, but obviously we do. So what do? We make it look easier by splitting it into a partial fraction, where we have the bottom. So each multiplied term in the bottom of the fraction, we would separate it out. So we have 2x plus 1, which is this one here, and then 2 minus 1, x minus 2 squared. And then we will also have an x minus 2, because we have the squared here. We need to split it out into x minus 2 and x minus 2 squared as well. So, and this would be our partial fraction for this function, or this fraction here. But we just need to find out what a, b, and c is. So a way to find a, b, and c is just to join this fraction back together. So we have the denominator as 2x plus 1 times x minus 2 squared. And we do this by either multiplying each of the terms. So for the first term, so say a over 2x plus 1, you would multiply by x minus 2 squared over x minus 2 squared. So you get the same denominator. So you would multiply the top and bottom by x minus 2 squared. And then for the second one, where you have b over x minus 2 squared, you would multiply the top and bottom by 2x plus 1, so you get the same denominator as well as this one. And then for the third term, you would multiply by x minus 2 and 2x plus 1, so you get the same denominator as well, and at the top you'll get 2x plus 1 and x multiplied by x minus 2. And then all we have to do is just compare the function at the top. So because we can add this up together so this can be the numerator of this one function, because you can just add the numerators together, because it's the same denominator. You can add these up all together and compare it to this, because it's the same as the denominator over here. So you write it out as this side of the function, which is the 8x squared minus 19x plus 1. And then you compare it to, so it's equal to this part all added up. And so first, to find one of the coefficients, which is a, b, or c, we can substitute any random x value to help us. So it would be helpful to eliminate the x minus 2 and make it equal to 0. So that's what we've done, because we have x minus 2 here and x minus 2 here, and it leaves us with no x minus 2 here, so this one wouldn't cancel out. So x minus 2 is equal to 0. We'll cancel out this and this, and when x minus 2 equals 0, our x is equal to 2, so we can substitute our 2 in all the x's here. So that's what I've done here, where I've substituted 2 in the left hand side, and on the right hand side, as you can see, the x minus 2 all become 0. So this one becomes 0 and this one becomes 0. While the coefficient of b, where I've substituted x as 2 from this, we get b multiplied by 2 times 2 plus 1. And then we have a nice expression in terms of b and this function over here, which should be pretty straightforward to find. So this all adds up to minus 5 when you collect all the, so multiply by 2 squared times 8 and then take away 19 if you put in your calculator, or just calculate it by mental maths. And then this side, you'll get minus 5. And then this side, when you do 2 times 2, which is 4, plus 1 equals 5. So the coefficient of b would be 5. So minus 5 is equal to 5b. And when you divide by 5 on both sides, so you can leave b on one side, you get minus 1 is equal to b. So you found out what b is already. And we can later substitute it into here. So all that's left is to find a and c. So how do we find another one, a? So we would make, instead of the x minus 2, 0. So instead of the x minus 2 equal to 0, we would make the other one equal to 0. The 2x plus 1 is equal to 0. So we can eliminate every term that has 2x plus 1. So over here, for example, and over here. So we're left with the a only. That is not equal to 0, or doesn't have a coefficient of 0. So it'll be pretty straightforward. So we rearrange the 2x plus 1, and we find that x in this case would have to be equal to minus a half. And we substitute the minus a half into the equation, and you see that the b coefficient cancels out and the c coefficient cancels out because of the 0 here. And you're left of an equation of just in terms of a, and all you have to do is just make a the subject. So this side, when you collect it all together, or solve for what this is, you're going to get 25 over 2, which is equal to 25 over 4 times a, which would be 25 over 4 would be this part here. And then when you divide by 25 over 4 on both sides, you find that a is equal to 2. So now we know what a and b is. All we need to know is now what c is. So for c, because c has both of the coefficients, as you can see, the 2x plus 1 and the x minus 2, you will have to use a different method instead of substituting a value for x, because if you eliminate this one, it will also eliminate this one because there's x minus 2 on both of them. And if you try to eliminate this one, it will also eliminate this one because 2x plus 1 is on this one as well. So what do? You compare x squared coefficients, which would make it a lot easier. Because we know what a and b is already, it will make it a lot easier. And because we see that there will be only x squared in the a, because x minus 2 is squared. So you will get, if you expand this out, you would get an x squared term. And if you expand this out, you will also get an x squared term, because 2x times x is equal to 2x squared. So when you expand this out, you don't really have to expand out the whole thing. You just need to know that the x squared term, what it is. So in the left-hand side, you see it's 8x squared. On the right-hand side, if you multiply the 8, so I expanded out just to see how it looks, but you don't have to do this whole step. You just know that x times x, because this is squared, was just going to be x squared. So the coefficient, so the term would be ax squared for this one. And you can ignore every other term because we're just comparing coefficients of the x squared term. And in this case, when you find the squared term of this, it will just be the 2x times the x, because no other combination would make an x squared term. So you'll get 2x squared and multiply by c, so 2cx squared. And you can also do it this way if you don't feel comfortable. Just expand it out all, find the x squared terms, and then multiply it out, and then compare coefficients. So the next step would just be to divide by x squared on both sides, and you'll be left with 8 is equal to a plus 2c, and then because you know what a is equal to 2 already, you found that out. And you substitute a as 2, and then you get 8 is equal to 2 plus 2c, and then take away 2 on both sides, you get 6 is equal to 2c, so you find out that c is equal to 3 when you divide by 2 on both sides. So now you know all the coefficients you can for a, b, and c. You can substitute back into the partial fraction, as we said before, and you'll find that the function that we had before simplifies into these partial fractions over here. And we can simplify this by just taking out the minus and leaving it outside here. And this is a lot easier to integrate. So this was the function we started with, and this is the function we're left with, which is the same thing basically. But this one is clearly a lot easier to integrate. And yeah, we can integrate this separately because we can integrate separate terms separately. So we can take out this fraction here, this fraction here, and this fraction here. And this one's really easy to integrate. We just use this formula here, where you have the ln form, where you have the differentiation at the top over the function at the bottom, and you get the ln of the modulus of the function plus c. So this red one here, that I've labeled red, becomes ln 2x plus 1. So pretty straightforward. We ignore the plus c because we have more integrations. We can just add the plus c at the end. And then we just have these two to integrate left. So for this one, we would have, so the ln, we will keep it the same. And this one's pretty easy to integrate. We just, because this is the function at the bottom, when you differentiate x minus 2, you get 1. And the same for this, by the way, when you differentiate 2x plus 1, you get 2. So that's why it fits this form here. And you can integrate this. And because the 3 on the outside, you've taken out the 3. When you take out the 3 on the outside, you don't really need to integrate that. So you leave the 3 on the outside and you get ln x minus 2 modulus. You can check this at the end if you're trying this question, and pause the video. And now we've integrated this part and this part. All that's left is integrating this part, which is a bit harder, but it's still possible using integration by substitution. And you make your u whatever's uncomfortable, so the x minus 2. So u is equal to x minus 2. And you find your du over dx again. So du over dx of x minus 2 is just 1, because when you differentiate x, you'll get 1. And then you rearrange this equation to get du is equal to dx, because you just multiply by dx on both sides, and dx is already made the subject. And then you substitute this all back into the equation. Your u is x minus 2, so you make your u at the bottom here, so 1 over u squared, because this would be a u in here. And your dx, you just replace it with du, because in this case, the dx is equal to du. And you can write it out like this. This is your integration for this. And this, you can write it even simpler as the integration of u to the power of minus 2, because when you do 1 over u squared, it's the same as u to the minus 2, because of exponential rules. And then when you integrate this, you increase the power, so minus 2 becomes minus 1, and divided by the new power, which is divided by minus 1. And then in the end, you get minus, so divided by minus 1 is the same as multiplying by 1, minus 1. So you get minus u to the power of minus 1. And now we just substitute whatever the old u was, and you get minus 1 over x minus 2, which was our value for u. And now we've finally integrated the whole function, where we found this using the f dash over f format, and this one as well, and then this one by using integration by substitution. And remember to add your plus c at the end always, because now we have the full integration. So because we have two logs here, we can use log laws. So the 3 becomes a power, and when you add two ln's, you can just multiply them together. So in the end, you'll get the ln 2x plus 1 multiplied by x minus 2 to the power 3, because the 3 becomes the power if you have a multiplied on the outside. And then plus the 1 over x minus 2 plus c. And if you're trying this question, pause the video and try it out yourself and just see the working out if you need to. So now let's move on to integration by parts. This is like the reverse of product rule. When you have a multiple of a times b, of a function a times a function b, and you're trying to integrate this, you would make your a u and your b a dv over dx. And this is very important to leave it in these forms. So one of your multiples becomes a u and another one becomes your dv over dx. And then there's always a priority for u depending on the whatever function it is. So if it's a logarithmic function, it has the most priority for u. So if a is a log and the b is something else, you would always make your u the log function. While if you have an algebraic and you have any of these two as your b, so always make your u your algebraic. Unless you have a log, obviously make it more priority. So log has the most priority to become a u. Algebraic functions have the second most priority to become a u. Trigonometric have the third most, and exponential have the last priority to become the u. So you need to prioritize this in order to get out a good result for integration by parts. And the formula is this. So say you have your multiple of a times b is the same as your multiple of u times dv over dx, because your a would be u and your b would be dv of dx. You would make it this, just for standard notation at the start, but you understand now. So once you make one of your functions u, you can differentiate it to find du over dx. So you can substitute the du of dx and the u into the function at the end. And if you make one of your functions dv over dx, you would integrate it to find v, so you can substitute it in the final function as well. So you can find it in the formula. So the formula is very useful to know, and it's the same as reverse product rule. So now let's do an example. So here they're asking to find the integral of x times cos x in terms of dx. And here it looks like a product rule because you have a function times another function, the x times the cos x. So here we would use integration by parts. And first let's look at priority, L-A-T-E, late, really good acronym to memorize. Your x is algebraic and your cos x is trigonometric, so the x gets the priority to become u. So you make your u x and your dv over dx is equal to cos x, because it's not, so u gets the priority. And then now you integrate this one and differentiate this one to find your du over dx and your v. So when you differentiate x, you get 1, pretty easy. And when you integrate dv over dx, or when you integrate cos x, you're going to get sin x, because sin x differentiates into cos x. And for this case, you don't really need to add a plus c, because we're substituting the values into the equation. And this is for integration by parts. And I've written down the formula, and now all we have to do is just substitute these values into the formula. So the formula is, so we multiply u, which is our x, times v, which is our sin x, take away a new integral of our v, which was sin x, times du over dx, which is 1, but 1 times sin x is just sin x, so I left it like this. So now all we have to do left is integrate this, which is pretty straightforward, which is just minus cos x. So x times sin x minus whatever was in here, which is minus cos x. We'll substitute that in, and then always add your plus c at the end. And now all we have to do is just expand the brackets out, and in the end we get x sin x plus cos x plus c is the answer to this integration here, using integration by parts. So pretty straightforward. Now let's try an even harder question, where they're asking for the integral of e of x times sine of x, where you have a product of e of x times sine of x, two different functions here. So first we do late again and see which one gets the priority. And as we can see, the trigonometric is sine x and the exponential is e of x. So the trigonometric gets the priority. So this will become u, and the other one will become dv of dx. So your u is equal to sine x, because of the priority, and your dv over dx is equal to e to the x. And when you differentiate sine x, you get cos x, so du over dx is equals cos x. And when you integrate dv over dx without adding the plus c, you get v is equal to e of x. So e of x, when you integrate and you differentiate it, it will always stay the same. So now we have all of these, we can just substitute into the formula. And when we substitute in the formula, we will get sine x as your u times v, which is e to the x, minus the integral of e to the x cos x. So times v, which is e to the x, and cos x, which is du over dx. So you multiply by cos x here, and then you still have this integral to solve. So now, because this is still a product of e to the x, a function, times another function, you need to do integration by parts again. So you do your late, and then your trigonometric function is your cos x, and your exponential is your e of x, just like before. So your cos x gets the priority for u again. And then so your u is equal to cos x, your dv over dx is equal to e of x. And du over dx, when you differentiate cos, you get minus sine. And when you integrate the e of x, you're just going to get e of x again. So now we have all our values, we can substitute again into this function. So using the formula, we find that the function is equal to cos x, e of x minus e of x times the minus sine x, because we substitute everything here into the formula here. And now we just expand it out, and we see that we still have another product here, but we're going to clear that later. So I've taken out the minus from this minus sine x, and this stays the same. So the cos x, e of x stays the same, and the minus and minus becomes a plus. So I've taken that out. However, this looks very similar to the question that we had. So the total, integration for the question that they gave us, which was this, is the sine x e of x minus this new integration that we found, which was the cos x e of x plus the integral of e of x sine x dx. And if we open up the brackets, we're just going to get sine x e of x minus cos x e of x. So just multiply the minus on both of these. And then we're going to get a function like this is equal to our question that we found, that we had before. So this is as far as we've gone with the integration. So another cool trick that we can do, instead of, because we have the question here and the question here, because we found it from this part here, we can just add both sides by this, and you're going to get 2 times the integral of e of x sine x dx. So because when you add this times this, because it's the same thing, it's the same as multiplying by 2. And you're just left with a very nice function here that you don't have to integrate anymore on this side. And this is the question here, this part, not the 2. So to find what the answer to the question, you can just divide both sides by half. So you're left with this. And remember to add your plus c because it's an integration, and this will be your final answer to the question, just by adding both sides of the question. So adding the question on both sides, and you get a 2 times the question, and then you divide by 2 on both sides. So you'll be left with no integration on one side, so you can find the final integration and add your plus c. And as you can see, this was the question that they asked us, and this is the answer that we found. And so if you don't understand how we got through this, I would recommend rewatching this again just to get good grips of it. But we didn't end up finding an integral on one side, so we just added integrals on both sides. So we left it on just one side. So we left one side without any integration. So we found the integral of the question. So we found what the question was, the answer to the question. So this is the end of the video. Thanks for watching, and I really hope this was useful for you. It was a very long video, but go back through any parts that you need to know, need to understand clearly.